can break my brain even more than you've already broken.
All right, let's do it. So I'm gonna share my screen. Hopefully, it's better availed than last time. So the rationale for why Haskell. The idea here is that, like, you know, if you like Google and Wikipedia programming paradigms, there is about 20 different paradigms that encapsulate the surface area of different ways you can think about programming. And I think, you know, we stay in the kind of reality is that almost all of us just use the one paradigm or one or two paradigms most of the time when programming. I think it's valuable to kind of like step outside of that domain and do something different now and then, just to get an understanding that like there are so many other ways you can think about programming than just the, you know, the OO or the imperative style that kind of is the stock standard.
Yes.
And so Haskell was a language kind of born out of the late 80s, where the problem was they had a bunch of, you know, so you can think of, there was this guy called Alonzo Church. He built this thing called lambda calculus, which is like an equivalent way of encoding computation to the Turing machine. And so there's a bunch of, you know, excitement and research that come out of the lambda calculus, and a bunch of people went off and implemented functional languages. But there was no, like, the problem that they were having was that there was no consensus on what language to use as like the research language. So for example, you might, you know, do a bunch of research and then have to like spend half your paper explaining how your language works because no one understands. There's no like one common functional language that everyone can kind of go like, I know how that works, and now I can just look at what's interesting about what you're doing. So Haskell is really just there to solve the problem of like, let's not keep like implementing the same kind of languages. Let's just have one that we can all agree on, and then we can kind of do research on top of that. So that's kind of the context as to where Haskell come from. And so I think today what we'll probably get through is syntax, and we might get into like one of the first kind of data types that is useful. So if you look at syntax, the nice thing about Haskell is there is like not much syntax at all, really. So we've got assignments. So I can say x equals true, and that's just an assignment, right? Or I can say y equals 10, s equals hello. And so all I'm doing is I'm just, you know, the standard, I'm just assigning a value on the right-hand side to some identifier on the left-hand side. So that's quite straightforward. What's probably a little more interesting is that if we think about type signatures. So let's say I want to write a function that just added 1 to a number. So in Haskell, you would write that. Oh, we got a question. We got a question on the forum.
Where?
He's coming through. I think
Oh.
Wait, do you have a question, Vita? Yeah, you do. Sorry, it's in chat.
Yeah.
I typed in third. Yeah, that's a very good question. So I'm just going to leave the chat there. So yeah, they are inferred, but you can say basically if the compiler can't work out what the type of this is, you can basically tell it by giving like a type hint and saying, actually this is a boolean, or in this case this is an int, or this is a string. If it couldn't work out what the type was. But yeah, you can, you know, I can say, if I said that was an int, the compiler would say, hang on, there's no way I can construct an int from this thing you've got here. So yeah, they're inferred. And so if we look at, like, for example, a function that you want to add 1 to the, so like, give me some number and I add 1 to it. A very simple function. So if we think about what's the type of that function, so we might say our function f, or let's say add 1, right? Our function add 1, this reads as has the type. So the function add 1 has the type that it takes an int and it returns an int. So we can just read this as takes an argument int and returns an int. And so if we had to implement that function, we would say add 1. Now this is where the little lambda comes into play. So we say add 1 equals a lambda, right, that takes some number n as the argument and calls n plus 1 on that argument. So that's how, that syntax here, the backslash says, okay, we're going to start a lambda. You can think of it like this.
Yeah.
Then I want to list some arguments, argument 1, argument 2, argument 3, whatever. Then right hand side of the arrow says, this is the expression that I'm going to, that's the body of the function. Arguments.
It's kind of like Lispy.
Yeah. And yes, on this case, we've only got one argument. And so it's quite straightforward. But there's a few different syntaxes. So that's the valid way you could say it like this. Or you could say, you could actually get rid of that. And you can say, I'm going to take the argument is on the left-hand side of the equals. So these two things are equivalent. Where you say, okay, add 1 takes one argument and then defines what the body is on the right-hand side of the equal sign. So there, for all intents, like what actually happens is that the Haskell compiler will desugar this one to this one.
Right.
That's just syntactic sugar for writing this. Okay, cool. So that's how you would define a function. Now, if we look at takes arguments, inline, lambda, cool. Okay, so that's all interesting and whatnot. But so now we could say something like this. What if you want to call add 1? You want to say add 1. We want to do what you would call like function application. So we want to say add 1 to. So I want to add 1 to. Well, let's say 3, right? I want to add 1 to 3. And so this would give me, comments in Haskell are just a double hyphen. So that would give me 4, right? So I could literally come here and just go, cool, replace n with 3. 3 plus 1, that's equals 4. So here we just applied. So here you would say I applied 3 to the function add 1. And you could write it like this. So instead of add 1, 3, you're actually, how you read it is add 1 is a function, and then we're going to apply the value 3 to the function, and then it will return a value. And if I had more arguments, so 4, 5, 6, 7, that's how you would pass the arguments through. So that's fine for add 1, but what about if we had, say, just a generic add? I take 2 ints and I return an int. So if you think about the type, takes an int, takes another int, and it returns an int. So it's not, you would think like, why isn't it like that, right? Why don't we just say like int and then returns an int, or or maybe we could say something like, some way to say like, oh, I just want 2 ints and then I return it. But this is kind of how Haskell's a little bit different to other languages. So this int, at first you're like, what is this int business? But how you read it is, so these arrows here, they just say, take an int to an int. Yeah, exactly. The old curry. So this is called, see this arrow here, this is called the arrow operator, right? And operators, like anything, have associativity, meaning that if I've got 1 plus 2 plus 3, addition is left associative, right? So it's 1 plus 2, then you go, where am I? Then you add 3 to the result of 1 plus 2, right? it's left associative. You would do the left hand first, and then you would do the right hand. But this operator here is right associative. So you do the right, you group the right hand first, and then you group the kind of outer expression. And so what this actually means is that add takes integer and returns a function that takes an integer and returns an integer. So, like, does that? I think like, have you come across the idea of currying before, Dave?
Yeah, I'm not very. It's not like natural, you know what I mean? It doesn't come naturally to apply it, but I definitely understand. You return a function with the first parameter essentially baked into the closure of that function, and then you compute the return function to apply the second parameter.
Yeah, I mean that's from a like an implementation, like because in like JavaScript and that you kind of you don't really have a choice. I mean to implement currying, yeah, you have to use closures to have that functionality, but Haskell kind of hides that away from you. You don't have to actually handle like it's like everything's curried by default. Okay. You don't have to do any work of like, oh, I'm just gonna like hold on to this value then return a function. It's like that just comes as a mechanism of the language.
Gotcha.
Because say all functions in Haskell only take one argument. There's no such thing as a 2-argument function in Haskell.
Oh.
And so even if I was like add 15 numbers and that was like int, you know, and I kind of went on, and then finally I had int, you know, what this really
kind
is.
Of like, sorry, go ahead.
No, you're going to say?
It's a bit like how Excel formulas work. Like they all take basically a single argument and you just wrap them around each other. So you might go, you know, sum of something and then wrap that around a sum of another thing and then an average. So, yeah, sort of nesting.
Yeah, totally. I mean, that's essentially what's happening here is that when you read this, what you're really looking at is add 15 that just a function takes one argument, an int, and returns a function that takes 14 ints. Like, you know, it's an int to a function, and then this function will take an int to another function. And then after you've got all 15 arguments, then when you call it, you actually just get the return value back. So that's kind of like quite a, you know, that idea of currying is like, it's kind of quite fundamental, right? If you like, because everything you kind of do, especially when you start getting into more abstract things, you know, the fact that things curry is kind of how you can make certain things work. So that's just worth kind of like lamenting on of like, that's kind of the mechanism.
Gotcha.
So if we think about implementation, the type for that function is exactly, it's the type for this function here is I'm an int and I return an int.
Yeah. Okay, gotcha.
So if I think about implementing this function, one way is if we do the like lambda style, I would say, okay, cool. I take, let's say, a being the first integer, and then I'll return a function that takes b, and then I'll return and then once I got b, I can return a plus b. So this is, I get the a, and then I take the a, and then I return a function that takes a b, and then when you call it with a b, I can return a plus b, right? Which is, you know, very much just like saying, you know, doing the a here, and then you return a function, takes a b, and then you return a plus b. Those two things.
But you have b. Oh, sorry. Yeah. Okay, gotcha. Sorry. Yeah.
So that's kind of those two things.
That's your JavaScript version.
Yeah, exactly. That's the JS version of what's going on here. But I mean, there's actually a few different ways you can write this. So you can, instead of doing this like, you know, lambda to lambda, the shorthand is to say, I'll just take 2 arguments in the lambda. add equals. Wait, Vito, is that like is that an implementation?
Oh, that's
that's like
arrow function version.
Yeah, that's a good point.
Yeah. Yeah.
Beautiful.
So, which is actually a good point, because it sort of shows you how it kind of marries up.
And those two things are equivalent at this point. And the only shorthand is you can just say, I'll pass the second argument, which will just sugar down to what we have here. Or what we have here, right? Or the other option is you just then say, you just pull it out of the left-hand side and say arguments A and B. I need A and B until I can call this expression A plus B. So these things are all equivalent. And I mean, you can even go one step further. You can say, I can pull out A, and then if I give me an A, I'll give you back a function that takes a B, A plus B. So all these four things are equivalent. There's this actually desugars to that, and these all will desugar to that at the end of the day. Does a function need to be typed? No, technically speaking, if I didn't add a type to the function, it could infer it, depending on the arguments. Like if I called it with, if I said add 1, 2, if it saw that, it would go, oh, okay, cool, that function A must be an int to an int. But you get in trouble if you did this and then you try to go,
hey.
It would be like, hang on, I don't know, is it int or is it string? I don't know what it is. So generally, people just write the type signatures, because it communicates your intention of how the function should work. So
does it have that concept like JavaScript where it will try to infer, if you do pass two strings, it'll be like, oh yeah, I can concatenate these, I'll concatenate them, or does it not have that?
So yeah, like conceptually, there are oh god, like that's a very good point that you made, because like it speaks to how Haskell thinks about abstraction. So you can think about abstraction in the OO sense. You might have like interface for like adding, and then you have to implement the adding interface, which means you have to define an append method. And then if I take something that implements the interface, appendable, then I can append those two things. Haskell uses like ideas from maths to build abstractions, as opposed to like using objects as the thing. So there are ways to achieve that, but it's more under a mathematical setting, as opposed to like we're going to go and implement an interface that does that. But yeah, you'll see there is like something that mimics the idea of like polymorphic types, where adding A plus B should be dependent on what A and B are. So I mean, this is kind of like, yeah, this is really, I mean, so that's functions.
Keep going on this.
No, you're right. So okay, that's cool. You got function. That's pretty. Oh wait, we got module resolution. How does module in Haskell? So basically, you can say module. This would be like syntax, and then if you do this, if I do that, that will basically wrap it out of global scope. Won't be. So if I didn't have that, it would be in global scope. And you'll see once we have like data constructors, you can actually say like, I only want to export some data constructor, and you can actually specify what it is you're going to export from this file. Vito's definitely got a question here. Yeah, basically, it's you name what things you want to export out of the context. Okay, cool. So we've defined this add function. So we would, again, just like with add 1, you would say add 1 and 2. That would give us 3, right? There's this nice thing in Haskell, which you can actually take any function and use it as an infix operator. So by that I mean you can say 1 with backticks. You can actually put the function in between the operators, or the operands, I should say. So those two things are equivalent.
That's unnecessary.
It kind of helps when like this actually is used quite a bit, because there are a lot of times when like structurally you want to be able to make it very clear that you have like a left-hand side and a right-hand side, but semantically they're the same thing.
Vito would like that.
What's that?
Vito would like that.
Yeah, just look at it. Wow, a little bit of add. But what's quite different to Haskell is that we could say, you know what, I don't want to type these 3 letters for add. That makes no sense. So we're going to define an operator or a function called we're going to have a function called plus bang, and it's going to be exactly we're going to implement add, but instead of it called add, it's just going to be called plus bang. And instead of now, we can just say I feel like so. Basically, what we've done here is we've yeah, because people start doing this. Got my starship. Then I've got my here for the. Yeah, it's pretty obvious what I'm doing, right? Like.
Yeah, if you can avoid any sort of strings at all.
Yeah. Just look up the type for that, and that should that's documentation.
Oh, it looks so familiar. I feel it right at home.
So basically, Haskell. We have 1 plus 2, but to Haskell, that's just a function called plus. I mean, they're not like functions and operators, and there's no difference in Haskell, right? Haskell doesn't discriminate between whether you're a function or an operator. You're all functions are operators, or operators are functions in that sense. And so if you looked at how add was defined in the standard library, it would literally just look like this. I mean, it wouldn't look like that because you're using plus to define plus, but maybe there was some other add method or something that could do it. So it's really important. Basically the rules are, if your function is not alphanumeric, it will be treated as a infix. Like you can use an infix that have to do the backticks. So add, you have to do backticks because it starts with A, but if it started with some symbol, then it'll be treated as, it'll be like infix by default. And to use say plus, for example, as a prefix, a normal function operator, like function call, you have to wrap it in the parentheses. So it's kind of like add to infix is backticks, and then a kind of a non-alphanumeric function to be used as a normal function is surrounded in parentheses. So that also would give us 3, right? So that's kind of like what you can do in terms of like the functions. That's about it. That's about all the syntax there is for functions. So does plus exist in the standard? Yeah, basically, like if I tried to redefine plus, it would be like, hang on, you've already got it. So like sometimes you'll see people, they'll put if they want to like re-implement the standard things, they'll put a dot there to try and like, emulate what it is that you're re-implementing. Or you might put a prime. So that's the other thing you can do in Haskell is I can say add prime is int to int to int, and then I can implement add prime as a plus b. So prime is a apostrophe is a perfectly fine, character in Haskell. Is someone else getting bad noise? Or is it Dave breaking up? Oh, I think.
What am I doing?
But I think is it my audio maybe?
Sorry, I don't know what's happening.
Can you hear me, Dave?
Yeah.
Vero, can you hear me? Oh, maybe I'm just getting a bit of feedback or something. So what's prime doing? So prime is just a way to say like I can't redefine add. It's already been defined. So add a prime to it to try and make out that's like it's a different version of add. It's almost like saying add v1 kind of thing. And it's just because in maths a lot of time someone will define a function and then you'll say f prime is some modified version of that function f.
Primo.
So that's really all the syntax for functions. The only other thing is like, okay, cool, you got functions, but how do you give values? No good if you've got all these functions, but you haven't got any values. Functions are just there to be computed over values. So in JavaScript we've got true and false. True and false. In Haskell we have true and false. But this is the beautiful thing about Haskell is that again, just like you can operators and functions, there's no real difference. The datas and the values. Jesus, I think my computers are wigging out pretty hard. Cool. They're back. What we can do is that if we take, say, true and false, they're type bool, right? But how would you construct something what is this bool thing that we're referring to? And what we're referring to is if you say data, right, you're saying, in this case, let me say like bool prime. So we're going to redefine prime if you like. Redefine bool. And we're going to say it equals true or false. So what we've said here is our type bool is either true or it's false. And what it might do is, if we jump in, say, what the hell? Resume. It said stop share. Share. Can you still see my screen?
Yeah.
Okay. It's just lying to me. So if we think about this bool thing, what's this bool thing? It says data structure not in scope. So it's kind of like if you look at what bool is false or true, right? Which means, so this is kind of what they call a sum type, right? So you think about data or values in Haskell, there's no objects, right? So how do you pass information around? And you pass information around using these things called algebraic data types. And algebraic data types basically fall into two categories. Either you're a sum type or a product type. So a sum type says I have to be one type or the other type. So an enum, for example, is a sum type, right? There's like a bunch, you might say like colors, and then you might have like red, blue, green, purple. Well, at any given instant, you can only be one of those values. You can't be red and blue or red and green. You've got to be red, blue, or green. So, you might say data color equals red or blue or green. Wait, I think I'm not saying anything further. Resume. If I stop, share. Is that better? Sweet. So if we say this, right, data color red, blue, green, we're saying I want to define some type called color, and it can only be red, blue, or green. It can't be. They're the only 3 values that this type can take on, which is kind of an important thing, right? Because if you think about, say, in JavaScript, if you take, say, even just like an integer or a number, right? Take like a number in JavaScript. It could be 0, could be 1, could be 2, could be 3. So when we talk about types, we're saying number is a type, right, in JavaScript. And there's only so many values that can be in that type. So here we're saying color only has 3 values in that type. Boolean only has 2 values in that type. So if I want to have a color, I might say color 1 is red. So now if I look at, let's can't do that for different reasons, but if I assign that to color 1 to red, what I'm saying is that that's the value. It's going to be a type. Well, let me just do it. If I look at the type of C1, it says it's color, it's type color. Because it's of the value is red, but the type is color. Is that, I feel, not saying data is like an enum. Well, okay, so that's because the reason this looks like an enum is because we only use some types. But I could say data person equals string and integer, say for their age. Yeah, so person in this case it's similar to a class in the sense you've got you can think of your data members as string and an int, but in an algebraic type sense, you'd be saying this is a product type. This is the product of string and int. So one possible value for this type would be, Dave 29. Oh, actually, I need to slightly got that wrong. So, okay, this is a bit of a weird thing, right? So here for color, red, blue, and green, they're all what are known as value constructors. So if you use red, it'll construct the value red. If you use blue, it'll construct the value blue. Now in this case, if you had a make person constructor, the data person, there is one of the constructors is make person, and it takes a string and an integer. So what is it saying? Not a data constructor. Oh, cool. You need to start with a couple. Okay, another weird thing about Haskell is that strings are just a list of char, essentially. But what we're saying here is that to make have a type person. Yeah, exactly. I mean, you can import data.string, and then you can say string instead of char. But gotcha. So okay, yeah, this kind of wigged me out for a bit. Like, what is going on here? I think it's almost more obvious if you say make person or make employee or make employer or something. And let's say for the case of the employee, you want to know their name and their age, but for the employer, you only care about the name. So now you could say, okay, cool. Let's have like employee 1 is going to be make employee Dave 24. So if you look at if I said, okay, what's the type of employee 1? What do we think?
It'll be person.
Okay, that's good. So the type, what we're doing, yeah, exactly. The type is person, right? Because data says I want a type called person, and here's how you construct all the values for that type.
That's pretty cool that you can do like multiple constructors for one class.
Well, it's because it really captures the idea of constructing values. And then what is particularly useful is when it comes to defining functions, you can pattern match on how you constructed a particular value. So if we now say, but if we say now employer one, and we'd say make employer, and that's just pick it. Now if you look at the type for employer one, it's also a person. So now imagine we wanted to write a function that just grabbed like if it was an employee, we'd grab the name, and if it was an employer, we'd just grab the name of the company. So it'd be like we have something called like some function called value of or something, right? And given a person, it returns a string. So to define that function, what we would say is, now you can't, you try to put in a type and it'll say, I don't know what you're talking about. There's no such thing as value of, so you've got to define it first in this case. But what we can say is we know what person is, right? So if you look at person, we know it's defined as two constructors, make employee or make person. Now we can say, okay, value of if, now this is a bit weird, right? If it was constructed using make employee, then you want to get the name and the age and just return the name. Right? Equation, what does it say? Make employee pattern. Oh, that's fine. It's just saying it's not exhausted. But there's another option, right? There was make employer.
Yeah.
And it didn't take a name and age. It just took the company name, right?
Yeah.
So in that case, we'll just return the company name. That's why it shows existing. Yeah, that's fine. So now we've kind of we've defined the two cases, and I think it's a little bit easier if we just for a second see what that looks like. So we said we had something called person that looked like this. And let's just, for simplicity's sake, say string, right? Now you want this function called value of, which takes a person and returns a string. So we have two cases, right? The first case is oh no, you can't say anything again.
So you're doing some off-screen prep.
That one. Is that better?
Oh yeah.
Cool. Yeah. So we've got person, our beloved person, and you want to create this value of function. So there's two cases, right? The first case is you used make employee to construct a person, and you gave them a name and an age. And in that case, we returned a name. Or the other option is that you used make employer, and you just used the company age. Oh, sorry, company name. Oh, come on. And in that case, you just return that. And so now if I say employee one is make employee day 24. If I say that, I get back Dave.
Yeah.
And if I say employer one, In this case, I get back picket because it has to basically pattern match on how was this value constructed. And that's kind of the big idea here, is that when you start defining things as this is so here what you have is you've got a product type, you've got this product type or this product type, meaning either it's string and int or it's a string. Can't be string int and string. It has to be either this or this. But even if you say make employee, you could say make employee, cam 18 or cam and 19. It's like these are all values. These are all the values that can be of type person, right? Or you could just have picket. Oh man, I gotta make employer picket. That's also a value. Or that's also a value. Like, so you can see here there's almost an infinite amount of values because string and integer are unbounded in a sense, right? You can I can give you cam 20 and I could just increment 20 to 21 and now I've got a new value that's of type person. But it'll only be ever in these two shapes. Either it's going to be a string int or just a string. And then by the constructor which one they used. So then you can define your functions as, oh, well, I just have to make sure I cover all the combinations, and that's how I'll implement a function.
Is that how I've never even looked at TypeScript really, but is that similar to what TypeScript allows you to do for JavaScript?
No, so TypeScript is TypeScript's more is at the type level, right, where you can say you can give a function a type annotation. But this pattern matching is kind of more, to do this pattern matching, you kind of need to have these algebraic types where you're saying things are, you could think of another example is data point. Is you could say,
int.
Exactly, int. So, point, that's a value, that's a value, that's a value. So they're all the values that are part of this type. But you need to have this idea of they call it a product type because all the values is the product of all the values for int times all the values for int. So if int was defined as 0 or 1 or 2 or 3 or 4, then the point type would only have 5 times 5 different values that you could take on ever. And so that's kind of conceptually int is defined as that. Is you'll see it written as essentially it's minus infinity.
Yeah.
Infinity kind of thing.
All allowable values.
Exactly. What happens if we return the value of a function differs between, what happens if the return value of the function differs between constructors? Return value. So any value of person, as in let's say we had a constructor that was make bad boy, and it
now you're talking.
It didn't have a name. Is that what you're saying? Per value
anonymous bad boy.
Person string name. Person string. Oh, so we define the function, right? So we'll always return a string given a person. If employee returns string, but employer returns int string. Well, see, we choose the semantic. So value of, in this case, we say we just grab the string from either one. But let's say make bad boy, for example, doesn't have a string, doesn't have a name. In this case, if we try to give it a value, make bad boy.
Yeah, so yeah, that's a good question.
And then we said well, we've only got age here. What do we do? Well, we have to have some default that's what do I do?
What if you
no name?
But what if you didn't have that value of there, Ken?
Which one?
Like if on line 2 lines down, what if you hadn't defined that yet and you created you made a bad boy, but you didn't have a value of pattern? Is that how I'm thinking about it? And I'm thinking about it correctly, it wouldn't work because if you hadn't defined.
Oh, if I didn't have this.
Yeah.
And then I tried to call value of bad boy.
Well, yeah, if you made bad boy, make bad boy, not an employer, down 4 lines.
Make bad
boy. Yeah. So then what happens if you ran value of bad boy there, would that throw an error? Because you can't find.
So this wouldn't compile. Haskell would say that your function isn't exhaustive. You haven't catered for all cases that could be constructed with.
Okay, I see.
So it kind of, that's exactly right. It does it basically, this has to be, this is essentially like a switch on all the ways you can construct a value. So generally you would say this is pretty normal. You usually, if you have one constructor, you would just call it the same name as the type. So I think maybe that's like probably a natural point to leave it.
Yeah. Interesting.
Because this is like, apart from type classes, this is about as much syntax as there is in the language.
Wow.
There's nothing like, there's no while loops, there's no for loops, nothing that, like, it's just functions at this point. It's just how you combine functions to get all that functionality.
So you have to like iterations all through recursion, or how do you?
Yeah, exactly. You do all iterations through recursion, and and then like there are ways to think about sequential computation that is done by combining functions. Like, you can think of what would it mean to be able to go like, I want to do this thing, then this thing, then this thing. Because right now, functions are just expressions, right? I just return name, or I might say name, and I might append bad boy to the end of the name, right? But they're expressions. There's no concept of like do this, then do this, then do this. And so there are ways to do that with kind of higher order kind of functions, if you like.
Composition type thing.
Yeah, you compose functions in a way that will have the semantics of doing this and this and this. But I think that's like, with that syntax under our belts, I think we could actually like start working through the exercises.
Cool.
All right. Well, I'll leave you and love you.
Thanks, mate. So the idea is, if we don't have something booked in future. Sorry, if we don't have an actual presentation, we just keep chipping away.
Yeah, we can just pick up and work through.
Okay.
And I don't think like, the fact, obviously we will probably forget a fair bit of stuff till the next time we jump back in. But I don't know, in some ways I think that might be helpful. Just like, from here, if you forget 95% of it, I think it'd only take a few minutes of like going back over it quickly to be like, oh yeah, okay, I understand. I remember how that works again, and then we can move on.